Calculus 2, Section 6.4, Areas of Surfaces of Revolution. That's important. These are not just areas like a blanket. That would be easy to figure out, a length times a width. But these areas are really, if you would take, say, instead, maybe a blanket, and put it on top of a solid. Say this solid is curved, and suppose, like a rope, you swing it around this axis, and this solid then, as you swing it around, really makes a bunch of circles. Well, these circles have a length, we'll call it delta S, and there are certain radius, you can call that R, I guess, so that you can take and add up all these strips. And if you add up an infinite number of those, then you can get this surface area generated by revolving something around this axis. Now, once you cut it down, I guess take all these and add them up, you're really looking at a little strip. This is the delta S, the width of that strip, the length of this piece right here. It's not the delta X and the delta Y like we were using before with volumes. This is a delta S, a length that we can use from our previous section, 6.3. But if you take then with this radius, this length or width, whatever you want to call it, is 2 pi r. So you can find the area of this strip using this 2 pi r, the width, times the delta S, that length. And then adding those up as we let the sum of all these lengths go to infinity. So the area then is 2 pi r delta S. Now it's important that this delta S be thought of not as like a delta X or delta Y. This is the difference of the areas. This is the area's nut. So it's I guess a length, not an area. This is the length up here that we're using. And if you remember from the section 6.3 that we can use the 2 pi r, let's use 2 pi y. That length is like 1 plus dy dx squared. So that we can find that length by using that length of a curve from section 6.3. And this 2 pi y is just then the circumference of this circle. So with that, we can then write 3 different forms of this. Let me change color so it's clear which these are. Okay. So we can have one of these, they still call it S for this area, the integral from a to b. Now there's going to be a 2 pi y, and then this 1 plus dy dx squared dx. This is really revolved about the x-axis. Now that makes sense because when you revolve around the x-axis, you're going to have that little thickness dx. If you revolve it around the y-axis, it's almost the same from a to b, but it's 2 pi x. Now if this makes sense, when you're revolving it around the x-axis, that y value is the radius. when you're revolving around the y-axis, the x value is the radius. And then we have to use our 1 plus 1 plus dx dy squared dy. Because now we got the thickness vertically. This is a 1. And we can do this parameter. Oh, this is about the y-axis. Now, we do have two forms. The third form comes in two parts. This uses the parametric equations. You can have 2 pi x or 2 pi y. How do you know the difference? Once again, it's a little bit backwards. The 2 pi x is about the x-axis, and the 2 pi y is about the y. Did I just say that wrong? Yeah, about the y-axis, and the 2 pi y is about the x-axis. So it still goes sort of with this. Revolving about the x, you need the y. Revolving about the y, you need the x. But it's that length that now changes. This is really x in terms of t, and this is y in terms of t. But this is the dx dt squared plus dy dt squared dt. Both of these are the same. Dx dt squared plus dy dt squared dt. The only thing different is the x and the y, and this is a function in terms of t. Instead of x in terms of y or y in terms of x, these are in terms of t. And they give you the radius. So there's 4, but really all of these are really the same. It's 2 pi radius and then the length of that little curve, that slice. So, how do you do these? Well, we're going to have examples of all three. So, this is Calculus 2, Section 6.4, continued, Problem 13, page 341. We're supposed to find the area of the surface generated by revolving this function from 0 to 2 about the x-axis. How do you solve these kind of problems? It's similar to when we were solving volumes, but this one, because it's an area, we have that formula that we can use. First of all, let's draw a picture. Because we know this is y equals 1/9 x cubed. And it goes from 0 to 2, then it does something like this. And we'll call this 2. Now, if this is revolved around the x-axis, then there is a bottom part to this. It's really like a horn, what do you want to call it? It's a cone. It's nothing. It's not filled up. This is not a volume. This is just the surface of that cone that we're finding. So, because we want to find that surface, we're looking for this strip. That is the delta S. And so, since we're doing this about the x-axis, we need the radius, which is a y, and do this delta x, or dx, if that makes sense. So we're going to use the formula from A to B. This is surface area. 2 pi y square root 1 plus dy dx squared dx. So, we've got the y. We need dy dx. Let's put that over here. So the derivative of this is 3 times 1/9 times x squared. So it's really 1/3 x squared, or x squared over 3. What is that squared? We need dy squared. So dy dx squared is x to the 4th over 9. And y is this x cubed over 9. So the integral goes from 0 to 2. That's what x does, because it's dx. 0 to 2. 2 pi, not y, but y is x cubed over 9, times the square root of 1 plus this dy dx squared, which is x to the 4th over 9 dx. Now, with a little bit of work, we get, pull out the 2, we'll leave it underneath there for right now. From 0 to 2, we have 2 pi x cubed over 9. This is then the square root of, well, I'm going to run out of room here, aren't I? Okay, well, let's write this once more. X to the 4th over 9 dx. But I'm going to do this in terms of u. I'm going to let u equal 1 plus x to the 4th over 9. Then du is equal to 4/9 x cubed dx. Well, I don't have the 4/9, I've got 2/9 x cubed. So I really need to make this a 2 if I want, see, how do I want to say this? I got to divide both sides by 2, so this is a 1/2. And then this will be a 2/9. Does that make sense? So, since I'm replacing the 2/9 x cubed with 1/2 du, so I've got the 1/2, and the du, and I'm replacing 1 plus x to the 4th over 9 with a u, so this is really just u to the 1/2. But I need to replace these limits of integration. I forget that often. Don't forget. So if x is equal to a 0, then u is 1. If x is equal to, so let's put that up here. If x equals 0, u equals 1. If x equals 2, then u is equal to, you put in a 2, where's that? It's 1 plus 2 to the 4th over 9, or 9 plus 16, I'm sorry, 9/9 plus 16/9, or 25/9. Does that make sense? Can I put that here? 25/9. So 25/9. Now, the antiderivative of u to the 1/2, we've done this a bunch of times. It's going to come up awful lot. It's u to the 3/2, because you add 1, then divide by 3/2, which is really times 2/3. Oh, I also have a pi in here. So this is, let's make sure I do this right. I've got a pi over 2 from 1 to 25/9 u to the 1/2 du. Okay. So now I get a pi over 2, and I've got the 2/3, because that's what I divide. pi, so 2/3. But it's u to the 3/2, and that's evaluated from 1 to 25/9. So these 2's cancel, and I get pi over 3. When I put in a 25/9 here, you're going to have to make sure you write this down maybe. The square root of 25 is 5, and the square root of 9 is 3. I get 5/3 cubed, which is 125/27. Minus, plug in a 1, it's still a 1, which is really 27/27. Does that make sense? So the square root of 25 is 5, cube it. The square root of 9 is 3, cube it. 1 we're changing into, because 1 to the 3/2 is just 1. We'll change it into 27/27. Altogether, that's what I'm trying to fit in here, is 90, times 3, we get 98/81 with a pi in there. Boy, it's hard to fit that on one page. I think with one page of your regular paper you can do that. But this is the key. So once you're given this stuff, figure out which form you need to use. And so you might need to have a way of memorizing that. Put in your x or y for your radius. Remember, if you're doing this with a parameter t, it would be y of t or x of t. Then put in your derivative for either x with respect to y or y with respect to x. Square it and plug that in underneath. Make sure that you change, once you change to the u, if you let u equal, like we did here, 1 plus x to the 4th over 9, change your limits. Otherwise, things are going to get messed up too. And take care of yourself. Go slow steps here. Write everything down. It doesn't matter that you've got a bunch written down. It's good. And then we'll do another problem. So we had a problem, number 13, where we rotated about the x-axis. Now we've got one that rotates about the y-axis. I've reduced the directions here a little bit because we're going to have certainly 4 steps. So if something is about the y-axis and you're given a function x in terms of y, then we should use the form s equals a to b 2 pi, about the y-axis we use x, square root, and since we've got this function in terms of x, we want the 1 plus dx dy, quantity squared, dy. So we need dx dy. What is dx dy? The derivative of x with respect to y. This is really 4 minus y to the 1/2. So it's 1/2 times the 2 times the 4 minus y to the negative 1/2. Or the 2's cancel. And this is 1 over 4 minus y. Square root, I guess, the 1/2. That's what dx dy is, but we don't want dx dy, we want dx dy squared. So if we square this, the 1 doesn't change, but the 4 minus y to the 1/2 becomes 4 minus y. So this is from 0 to 15/4. 2 pi, we don't want x, we need this 2 square root of 4 minus y times the square root of 1 plus 1 over 4 minus y, because that's the dx dy squared, dy. Whew. Now, if we bring this square root, put these square roots sort of together, this goes from 0 to 15/4, 2 pi. I'm going to make this 4 pi, sorry. These twos I'm going to put together. But this 4 minus y is going to multiply the 1, so it's a 4 minus y. Plus, and the 4 minus y will multiply this, which is really just the 1, right? Because the 4 minus y's cancel, dy. So we've got the integral from 0 to 15/4 of, let's see, 4 pi, and this is just the square root of 5 minus y. dy. Okay, once again we're going to run into space issues here, but in order to find the antiderivative, I'm going to let u equal 5 minus y. Then du is equal to a negative dy. Well, I don't have a negative dy, so I'm going to need to put the negative over here in the du. Also, when u equals 0, then, when y equals 0, then u equals 5. When y equals 15/4, then u is equal to 5/4. 5 is 20/4 minus 15/4, which is 5/4. So those are going to be our new limits. This is going to be the integral from, let's see, the 0, which is 5, to the 15/4, which is now 5/4. U, but this is, we need the negative du, so I'm going to put a negative out front. Then it's u to the 1/2. Oh, where's the 4 pi? To the 1/2 du. Now, when you've got a negative integral, remember, you can switch the limits of integration, and we'll get rid of that negative by putting the 5/4 as the lower limit and 5 as the upper limits of integration. Then the 4 pi and u to the 1/2 du. Okay. So let's see here. We have 4 pi. I'm not sure I can fit all this in, but we'll see. We have the 4 pi. The antiderivative of u to the 1/2 is, once again, 2/3 u to the 3/2 from 5/4 to 5. So we're going to pull this 2/3 out. This is going to be 8/3 pi, or 8 pi over 3. Plug in a 5. Well, the square root of 5 cubed is really a 5 times the square root of 5. Does that make sense? The 1/2 is the square root of 5, then you cube it, so you've got one square you can pull out and one 5 you have to leave. The 5/4, the square root of that, I might have to write that out. 5/4 to the 3/2. So you get 8 pi over 3 the square root becomes the square root of 5 over 2. But this is 5 square roots of 5 over 4 then, because, I'm sorry, over 8. Gosh. Yes. So this is 5 square roots of 5 minus 5 square roots of 5 over 8. Because the square root of 4 is 2 cubit. Oh my gosh. Barely fits. This is really 40 if I want to do this over 8. 40 square roots of 5 minus 5 square roots of 5 is really 8. Oh, I'm sorry. These 8's cancel. So 40 minus 5 is 35 square roots of 5 times pi over 3. Oh, gosh. Can you see that? 35 square roots of 5 pi over 3. Man, I got to write smaller. Okay, let's do one more, though. Does that make sense? Once again, figure out which form you're going to use. Find out what you're going to load in there, but that's how it helps you figure it out, too. You're given the x. You're given what that y is between, so you know it's with respect to y. Let's do another one. Okay, I didn't mention for that last problem that you probably should have graphed it, but I will mention it for this problem because I want to make sure you guys know how to do this on your calculator. If you got your calculator, you need to, first of all, not use the y equals, if it'll work here. I hope this mode, let me stall this for a second. Okay, I got it working here. So press your mode button to get to parametric mode. Then when you press y equals, you will get this x sub 1 of t equals y sub 1 of t equals. And these then you write in. I'm going to do this, you noticed I probably had it done before, in parentheses 2 divided by 3, and then t, but I'm going to use, when you click the x button in this mode, it gives you a t, to the, and the 3/2 power, put that in parentheses. So it looks a little bit weird. In parentheses 2/3 t to the in parentheses 3/2. And then we want 2t to the 1/2. Now you can put in just 0.5 if you want to. You can put in the 1/2 as a fraction, but I would use parentheses. I think it might be very important for that. When you click your window, this is supposed to go from 0 to the square root of 3. And when you put that in, it gives you the decimal approximation for that. The t step is how, I guess, how it counts. 1/10 is usually pretty good. You can sometimes make it bigger, but you can't make it too big or it's going to skip on past things. Especially going from 0 to 1.7. This is going by tenths. It's not too bad. Now I've got this x min and x max, -5 to 5, with a scale of 5. I've also got the y min and y max, -5 to 5, but I played around with that to see what it would be. So you don't always know. -10 to 10 for each of those can be the best place to start. When you graph, you get this. Now that means that I really just want this portion of the screen. And sometimes when you click your zoom, it's easier with ZBox. If you can see the cursor here, you sort of spread out a box. Let me go away from the axis. This little plus sign will be the corner of a box. A little bit higher, press enter, and then you stretch it out. I'm going to go a little bit past that end and then stretch this down to get below the x-axis. And now it'll make the screen that size, which is not so bad. So it's taking this curve from 0 to the square root of 3 and wrapping it around, in this case, the y-axis. Yep, the y-axis. So this is going to look more like I guess a cone, a funnel, something like that. But I think it'll come down to a point here, because it should be at 0, it should be 0. So now that you know what it looks like, you can put this away and draw a picture. So this is going to be essentially a really tiny picture, but it's going to be a cone. It goes around, it looks something like that from 0 to square root of 3. So this is why you should say, okay, around the y-axis. Then I need the form from a to b, 2 pi. If it's around the y-axis, I need an x. Square root, since I've got parametrics, it's dx dt squared plus dy dt squared. So what is dx dt? Well, this is 3/2 times that, so it cancels. T to the 1/2. What is dx dt squared? It's just t. Does that make sense? But it's really not just t, it's the absolute value of t. Now the absolute value of t is not a problem because t goes from 0 to the square root of 3, and so we don't have to worry about that too much. What about dy dt? Well, this is 1/2 times 2, so it cancels, and 2 to the t to the negative 1/2. So this is going to be, when I square this, dy dt squared is going to be t to the negative 1. It's really 1 over t. Now that might be a problem when you plug in a 0, but it's sort of nice to know that this function, the function here, the function is here, these two. As t goes to 0, this function goes to 0. So it's defined at that point. There's no problem at that point. There's no division by 0, even though this has within it that 1 over t. So we're going to take our s. This is going to go from 0 to the square root of 3. 2 pi, not x, but 2/3, t to the 3/2. Square root, this is the t, we don't need the absolute value because it's always positive, plus 1 over t dt. So we've done a lot of stuff right there. We can pull this 4/3, well, I'm going to leave the 2t here because I'm going to need that later. Let's do that now. So we're going to let u equal the t plus t to the negative 1. So du is 1 plus the derivative of t with respect to t is just 1, but here you're going to take a negative 1 and it'll be to the negative 2. Now, the reason I did that is because it always seems like we take this thing and make it our u. But when you take the derivative and you get something like this, 1 minus t to the negative 2, and you don't have that here for part of your dt stuff, then you've got to wait. Just take a minute here. So, I'm not going to really use that because I've got to do a little more work with this first. I'm going to take this t to the 3/2. Really, this is, let's write this as 2 pi, and then this is 2/3. This is really t times the square root of t, times the square root of t plus 1 over t dt. Okay. And the reason I'm going to do this is so I can pull this t underneath with these others, because they're both square roots. So now this is from 0 to square root of 3 of 2 pi, the 2/3 t, and underneath becomes t times t, which is t squared, and t times 1 over t, which is 1 dt. Now we let u, so let me get rid of this. I'm seeing if I can get the eraser. Now u is t squared plus 1. So du is 2t dt. And here I've got a 2/3 t, so I'm going to put that 3 with that. This is 2 pi over 3. Here's the 2t dt. That's going to be my du. And here's t squared plus 1, so this is my u to the 1/2. Same old problem to figure out here. So I've got 2/3 or 2 pi over 3. This will be u to the 3/2 times the 2/3 from, I need these limits. If t is equal to a 0, u is equal to a 1. If t is equal to square root of 3, then u is equal to square root of 3 squared, which is 3 plus 1 or 4. So this is going to go from 1 to 4. And now I can write this, let's see. This becomes 4/9, 4 pi over 9. Plug in a 4, take the square root as 2, cube it, it's 8. Plug in a 1, take the square root, it's 1, cube it, it's 1. So 7 times 4 is 28 pi over 9. So, hopefully those 3 examples give you an idea of what's going on here. You're going to be trying to get that square root. Make sure it's something, as this one did, that's got something on the outside. So be a little careful. Maybe try to reduce this as much as you can. It may take several tries. Don't give up. Just try it again. That is section 6.4. Hopefully you'll have enough examples. If you need one, though, make sure you let me know, and I'll see you after this.